This is Dr. Shankaraiah from Department of Physics. In today's presentation, I am going to discuss about definition and terminology on Module 1 of Applied Physics, which is crystal structures. So, the first question is, what is crystallography? The definition of the first one is, what is crystallography? So, answer for that is the study of geometric form and other physical properties of crystalline solids by using X-rays, electron beams and neutron beams constitute crystallography. Okay. So basically crystallography is nothing but a study of materials. We are going to look at the given material, and we are going to say whether the given material is a crystal or amorphous material using different techniques. For example, we can use X-rays, we can use electron beam, we can use neutron beams to find out whether the given material is a crystal or amorphous material. Okay, so all these studies about these material structures is nothing but the crystallography. What is a crystalline solid? Okay, so in crystallography we can find out whether the material can be a crystalline material, it can be amorphous material. So the next question is, what if you are saying that the given material is a crystalline material, what is the meaning of a crystalline solid? A crystalline solid is formed by regular repetition of its building blocks, okay, in a three-dimensional periodic array. So crystalline solid is nothing but a regular repetition of its building blocks. For example, the building blocks can be atoms or molecules. Okay, so I have a crystalline solid where the building blocks of the crystalline solids are atoms. Okay, so all these atoms are arranged in a regular periodic manner. Okay, so all these atoms are arranged in a regular periodic manner. Okay, such a such a solid is called as crystalline solid. Crystalline solid is nothing but the atoms or molecules, the constituents of such a crystalline solid are arranged in a regular periodic manner. Then that solid is called as crystalline solid, and the distance between any of these two atoms along x-axis, for example, is constant. Okay, so and the distance between any two atom along y-axis is also constant. Okay, so here examples are also given. Crystalline solid examples are NaCl crystal. You can take nickel crystal. Also, many of the metals, ice and ceramics. All these are examples of crystalline solids. Okay, next is, what is amorphous solid? Okay, so we have discussed what is crystalline solid, and then what is amorphous solid. Amorphous solid is a material in which constituents are not arranged in a regular manner over a long range. Okay, so amorphous solid is also a solid in which the atoms are arranged. They can be arranged in a regular manner, but not for over long distance. Only very short distance they can be arranged in a regular manner, but then they are all arranged in non-regular manner. Okay, so amorphous solid is a solid in which atoms are not arranged in a regular manner over a long range. Amorphous solid is a solid in which atoms are arranged in a regular manner over a short range. You can define that. Or amorphous solid is a solid in which atoms are not arranged in a regular manner over a long range. Okay, so that is amorphous solid. There is no periodicity because the atoms are arranged only for a short distance. That is why there is no periodicity in structures. And if periodicity occurs, it must be over a short distance. Even if you find there is some periodicity, then it is only for a short distance. Okay, so the examples of such amorphous solids are crystalline, amorphous solid examples are glass, plastic, rubber. Glass, plastic, rubber, some of the examples of amorphous solid. Amorphous solid is a solid in which atoms are not arranged in a regular periodic manner. Okay, so we have discussed two different types of materials. So in crystallography, using crystallography, you can study both, you can classify the materials as amorphous crystalline solid by using X-rays, electron beam or neutron beam. And now we have discussed what is a crystalline solid and what is an amorphous solid. Okay, so to next definition is define lattice. So what is lattice? So to understand these material structures, whether it can be a crystalline solid, it can be amorphous solid, we are going to use some theoretical basis, that is lattice theory. So to start with this theory, we are going to define a lattice. Okay, to understand crystalline or amorphous materials, we are going to use some theoretical basis, and in this theoretical basis, we are going to first define a lattice. So lattice is defined as a regular periodic array of points in space. Each point is in a lattice has identical surrounding everywhere. Lattice is basically imaginary points on space with a periodic manner. Okay, so when I look at the crystalline solid, for example, using X-rays, I will find that all the atoms are arranged in a regular periodic manner. For example, NaCl crystal, so I have Na atom here and Cl atom here, again Na atom, again Cl atom. Okay, so there is a periodic arrangement of Na atoms and Cl atoms, and then that is a NaCl crystal. But I want to study of this NaCl crystal using the theoretical basis. Okay, so I'm going to define something which has this regular periodic arrangement. So that is what is called as lattice. So lattice is nothing but points, imaginary points which are arranged in a regular periodic manner like a crystalline solid. Okay, so that is what is a lattice. And you can define lattice in 2 dimension, and you can define lattice in 3 dimension. Materials are in general 3 dimensions. So we are going to define lattice in 3 dimensions to understand the materials, real materials. Define space lattice. Atoms in a crystal is replaced by a point in space, then the resultant points in space are called space lattice. Space lattice or previous lattice are nothing but this lattices where atoms in a crystal is replaced. So we are trying to understand a crystal. So in crystal you have different atoms. Na crystal, you have Na atom, Cl atom. So we are going to replace this Na atom by one point, Cl atom by another point. So you basically replacing these atoms by points in space. So that's why you are calling this lattice as space lattice. How basis is formed? So we have defined lattice, space lattice, and then we came to this basis. Atoms are molecules which are constituents of a crystal material, okay, or nothing but a basis. Okay, so for example, I want to understand NaCl crystal. So you have Na atom, then you have Cl, chlorine atom, Na atom, and then you have chlorine atom. So this is the, okay, again you have Cl, Na like that. So first, to understand this material, I have defined a lattice where I have replaced these atoms by points. Okay, I got these points. But what is the use of these points? Okay, so then this is, I have defined this as lattice, space lattice, because I have replaced the atoms by mean position of each atom I have replaced by a point. So then I call this as space lattice. Okay, then I want to attach each lattice point an atom, for example. So I am going to attach sodium atom here, chlorine atom here, sodium atom here, chlorine atom. Okay, so then that atom or a group of atoms that are attached to each lattice point is called as basis. Okay, so these are the constituent of this space lattice. Okay, so atoms are molecules, or atom or a group of atoms that are attached to each lattice point is called as basis. So then next, to coming to unit cell. Okay, so we have defined lattice, space lattice, basis, and then unit cell. What is this unit cell? Unit cell is convenient to divide the crystal into small entities. Such small group of atoms or molecules is a well-defined arrangement. These small cells are called as unit cell. So unit cell is basically the smallest geometrical unit. Okay, so I am defining it here. Unit cell is the smallest geometrical volume actually. So smallest geometrical volume by repetition of which can generate the crystal. Repetition of which can generate the crystal. Okay, so smallest geometrical unit, geometrical volume by repetition of which you can generate a crystal. For example, you have okay, you have NaCl or any crystal, any crystal. So if you have NaCl crystal, for example, Na atom, Cl atom, Na atom, Cl atom, okay. Okay, so this is in 2-dimension. Okay, now I am going to take this smallest geometrical unit. Okay, this smallest geometrical unit. So this is NaCl and Cl and Na, right? So Cl and Na, for example. So this is my basis. This is my unit cell, and I am going to repeat this. Again, I have NaCl. Again, I have NaCl, Cl. Okay. So the smallest geometrical volume, by repetition of which, again, so next when you look at NaCl, Cl, again next you repeat NaCl, same structure is repeated. Such a small structure is called as unit cell. Okay, so we are defining unit cell as the smallest geometrical volume, by repetition of which you are going to generate the whole lattice. And if you understand this unit cell, you will get more complete information about the lattice or crystal. Okay, so that is what is a unit cell. Okay, so the next one is differentiate between primitive and non-primitive unit cell. Okay, there are different kinds of unit cells. You can have primitive unit cell and you can have non-primitive unit cell. So what is a primitive unit cell and what is a non-primitive unit cell? So primitive unit cell is nothing but the one number of atoms per unit cell must be 1. Number of atoms per unit cell. Okay, so let me write it clearly. So primitive cell is number of atoms per unit cell must be equal to 1. If number of atoms per unit cell is 1, then we are going to call that as primitive units. Non-primitive unit cell are the ones which have number of atoms per unit cell more than 1. Those are called as non-primitive unit cell. Okay, so that is what is given here. The unit cell formed by primitives is called a primitive unit cell. A primitive unit cell contain only one lattice point, one atom per unit cell. And if unit cell contain more than one lattice point, then that is called as non-primitive units. Okay. So what is meant by lattice parameters? So we have defined unit cell, right? So unit cell, for example, in 3-dimension, you have defined a cubic unit cell, for example. So I have a cube. Right, so I have a cube. So this is cube. So this is my unit cell. So I need to look at so there is one atom here, one atom here, one atom here, here. If it is a simple cubic unit cell, so I have 1, 2, 3, 4, 5, 6, 7, 8. 8 atoms are there. Okay. So I want to look at the distance between two atoms along x-axis. So the distance between the two atoms may be A, this is x-axis, and the distance between two atoms along y-axis also I want to know, so that is B. The distance between along z-axis also I want to know, that is C. Okay, so A, B, C are the distance, okay, axial lengths are the distances between any two nearby atoms. Okay, ABC. And then also I want to look at what is the angle that is made by y-axis with x-axis. So that is alpha. What is the angle made by y-axis with z-axis? Beta. What is the angle made by z-axis with x-axis? That is gamma. So the axial lengths and interaxial angles ABC and alpha, beta, gamma, all these together are called as lattice parameters. These ABC are also called as translation vectors, and interfacial angles are nothing but alpha, beta, gamma. Translation vectors are nothing but ABC. So both translation vectors and interfacial angles both together are called as lattice parameters. So these lattice parameters are important to understand about the unit cell. And if you understand about a unit cell, you can understand more about a crystal. Okay, so the 10th one is, what are the important parameters that are used to describe the crystal structure of materials? Okay, so we need to understand the crystal structure of materials. So what are the important factors, parameters that we need to use? Okay, so the answer is effective number of atoms per unit cell. That is nothing but the number of atoms per unit cell, maybe Z. I am denoting it by Z. Atomic radius. You also need to know what is the atomic radius. You also need to the coordination number. Coordination number, you can define it as by capital N. So number of nearest neighbors is nothing but coordination number, and nearest neighbor distance. Nearest neighbor, what is the distance between any two nearest neighbors? So that is nearest neighbor distance. Atomic packing fraction. What is the atomic packing fraction? and what is the volume that is occupied by the atoms in a unit cell, and interstitial space are dense. Okay, this is nothing but the void space or empty space. So atomic packing fraction will tell you the occupied volume. What is the volume that is occupied by the atoms, that is atomic packing fraction, and what is the remaining space, that is nothing but the interstitial space or void space, and then finally you need to know the density. So these are the important parameters to describe the crystal structure of any material. Then the next question is how can you define the effective number of atoms per unit cell? Okay, so these are the important parameters we said to understand the material crystal structure of materials. Then the first question is how can you define effective number of atoms per unit cell? Z. Okay, so the effective number of atoms per unit cell is the total number of atoms in a unit cell by considering the contribution of corner atoms, center atoms, and face centered atoms. So to calculate the number of atoms per unit cell or the effective number of atoms per unit cell, you need to look at the contribution from the corner atoms, center atoms, and face centered atoms. Suppose if you have a body centered atom, so you will body centered lattice, BCC, body centered cubic lattice. So there is atom present in the body center of this cube. So that should be considered. What is the contribution of this body centered atom? For example, you are considering face centered cubic lattice. So there will be atom in each space, center of the face. So you need to also consider the contribution from the space centered atoms. So to define the effective number of atoms, not only you consider the contribution of corner atoms, but also in addition to this, you also need to consider the contribution from the body centered atoms if it is there, also face centered atom if it is there. Okay, so that is the effective number of atoms per units. So the next one is what is atomic radius? How do you define atomic radius? Atomic radius is halfway of the distance between any two successive atoms in a crystal lattice. Okay, so if you are taking any cubic lattice or other lattice, suppose I have taken this cubic lattice, so there is one atom here and one atom here. Okay, so I am going to take to define the atomic radius. Atomic radius is nothing but the half of the distance between any two consecutive atoms. So you need to select a direction. You need to select a direction in which atoms are in contact. Then you define half of the distance between any two consecutive atoms is defined as radius. Once you define the direction along which two atoms are in contact, then you can define the distance between these two atoms is this. Then half of this is nothing but so this is the total distance between the centers of these two atoms. Then half of them is nothing but the radius of atom. Okay. So that is how we define atomic radius. Define coordination number. Coordination number, the number of equidistant neighbors that an atom has in a crystal lattice is known as number of coordination number of nearest neighbors. So coordination number is basically how many number of nearest neighbors are there for a atom. So that is nothing but the coordination number. Then what is crystal plane? Okay, what is crystal plane? So the crystal plane, the plane passing through the lattice points is known as crystal plane. What is a plane? Plane is nothing but you have a lattice points and the plane passing through all these lattice points is nothing but crystal. What is interplanar spacing? The perpendicular distance between any two adjacent atoms, crystal planes, is called as interplanar spacing. So I have a plane here. So this is the plane passing through these atoms and this is the plane passing through these atoms, and the distance between these two atoms is the interplanar spacing. Okay. How the crystal systems are classified? Crystals are classified into 7, okay, based on the shape of the unit cell or lattice parameters. So how did we classify the crystal system? We classified the crystal system into 7 systems based on shape of the unit cell and lattice parameters. So we have defined lattice parameters A, B, C, alpha, beta, gamma. So based on these relation between these, we have classified the crystals into 7. Mention the 7 crystal systems. So what are these 7 crystal systems? Cubic, tetragonal, orthorhombic, monoclinic, triclinic, rhombohedral, and hexagonal. So these are the 1, 2, 3, 4, 5, 6, 7. So these are the 7 crystal system that we have classified based on lattice parameters and shape of the unit cell. So the next question, what is crystal structures? The particular repeating arrangement of atoms throughout a crystal is nothing but the crystal structure. Okay, a structure in which there is repetition of atoms throughout a crystal, that is nothing but the crystal structure. Basically, you see a structure in which you have repetition or repeating arrangement of atoms throughout the crystal, that is called crystal structure. Define single crystalline solids. Okay, so a crystallite is a domain of solid state matter that has the same structure as a single crystal. Okay, a crystalline is a domain of solid state matter that has the same structure as a single crystal. So single crystal is nothing but throughout the lattice you have the same arrangement or same repetition of atoms. Okay, so there is a periodic arrangement of atoms throughout the crystal, then we are going to call that as a single crystal. What is a polycrystal? Okay, polycrystalline materials are solids that are composed of many crystallites of varying size and orientation. Crystallite is nothing but a small size, small volume in which you have regular periodic arrangement of atoms. Okay, so polycrystalline, if you take a polycrystallite, there is no periodic arrangement throughout the lattice, throughout the crystal, but there are crystallite present in this crystal, and somewhere there is the atoms are regularly arranged here. But then there is another crystallite, again there is regular arrangement of atoms. There is another crystallite, again there is arrangement of. But throughout crystal there is no regular arrangement of atoms, but there are crystallite in which you have this local order. Okay, so that is called periodic polycrystalline solids. Okay, so polycrystalline solids have different sizes and orientation. So here the orientation can be different, here the orientation can be different, here also the orientation can be different. So the orientation of these crystallines is different. So then what are Miller indices, or what is a Miller index? Okay, Miller indices are set of three integers which is used to designate the three different crystal planes in the crystalline lattice. So Miller indices are nothing but the set of integers, three integers HKL, which are used to designate the crystal planes. To designate a crystal plane, we use set of three integers, which is called as Miller, which are called as Miller indices. Define lattice plane. Okay, a lattice plane is a two-dimensional array of points showing how atoms are arranged in the lattice. Okay, so lattice plane is nothing but a two-dimensional array of points showing how atoms are arranged in the lattice. So that is lattice planes. What are Miller indices? Coordinates. What are the coordinates of these Miller indices? Miller indices are three-digit notations that indicate planes and vectors within a crystal. Okay, these notations are based on the Cartesian coordinate system of XYZ. The Cartesian coordinate system is illustrated using three vectors XYZ. Okay, so Miller indices to coordinates are nothing but the Cartesian coordinate system XYZ. Okay, so we use these Miller indices to designate or to denote a plane. How Miller indices are denoted? A general Miller index is denoted by HKL. If a plane has negative intercept, the negative number is denoted by a bar on the number. Okay, so if the Miller index is positive along positive axis, XYZ axis. Okay, so if this is the plane, okay, so yeah, so if let me draw the positive HKL. Okay, so HKL. So this is x-axis, y-axis, z-axis. Then I have a plane like this. Okay, so then that is positive HKL. Suppose if I have a negative intercept along one of the axis x, y, z. Okay, I have a negative intercept. Okay, then I am going to put a bar on K, because along y-axis, suppose if it is along y-axis, that along z-axis, if I have a negative intercept, then I am going to put a bar on the index corresponding to that coordinate system. Okay, what are Miller indices and unit cell? Miller indices are a method of describing the orientation of a plane or a set of planes within the lattice in a relation to the unit cell. Okay, in a unit cell, we can look at the orientation, position and orientation of a plane using these Miller indices. What is a Bravais lattice? Bravais lattice refers to the 14 different three-dimensional configurations in which atoms can be arranged in crystals. Bravais lattice is nothing but the lattices which are used to describe the crystals. That means these lattices have regular periodic arrangement of atoms, and there are 14 such Bravais lattices described by Bravais. What are the 14 Bravais lattices? There are 7 different ways to group the 14 Bravais lattices. The 7 crystal systems are triclinic, monoclinic, orthorhombic, tetragonal, rhombohedral, hexagonal. So these 14 different types of lattices, okay, so different types of arrangement of Bravais lattices. There can be body-centered cubic lattice, there can be cube-centered cubic lattice, there is simple cubic lattice. Similarly, each crystal system has different types of Bravais lattice. Cube itself has 3 Bravais lattices. Similarly, other crystal systems also have different types of Bravais lattices. Altogether, there are 14 Bravais lattices available. What are the 7 Bravais lattice systems? Okay, so the 7 Bravais lattice system or lattice crystal systems are discussed already: triclinic, monoclinic, orthorhombic, tetragonal, rhombohedral, hexagonal, and cubic. What is the Bravais rule of lattice? The Bravais rule proposed by M.A. Bravais states that the density of these lattice points or spacing between lattice planes is proportional to the relative importance of the crystal forms. Okay, so the Bravais rule states that the density of the lattice points, the density of the number of atoms in a unit cell, or the spacing between lattice planes is proportional to the relative importance of crystal forms. Okay, so it's very important to identify the density to define this Bravais lattice, because density or the distance between planes is important to define different types of crystal forms. So that is a rule used to describe different arrangements of lattice points. What is hexagonal Bravais lattice? The hexagonal lattice has a primitive cell. For this lattice, A is equal to B but not equal to C. And also alpha is equal to beta is equal to 90 degrees but gamma is 120 degrees. So this is the hexagonal crystal system. Which has more Bravais lattice? Which has more symmetry? Which has the crystal system which contains more than one Bravais lattice is monoclinic. Okay, so which has more Bravais lattices? So monoclinic system has more Bravais lattices. What does the interplanar spacing depend on? Interplanar spacing, which is the separation between set of parallel planes formed by the individual cells in a lattice structure, depends on the radii of the atoms forming the structure as well as the shape of the structure. That is interplanar spacing depends on planes as well as radii of atoms. Okay, what is the interatomic and interplanar distance? Okay, so interatomic distance is the distance between two adjacent atoms in a plane, and interplanar distance is the distance between two adjacent planes in a crystal. So these are different. What are the planes and directions in FCC structures? In the FCC, the closely packed plane is 111 and the closely packed direction is 110. What is a crystallographic direction? It refers to the directions in the various crystal systems that correspond with the growth of the mineral and often with the direction of one of the faces of the original crystal itself. Okay. Crystallographic direction is nothing but directions in various crystal systems that corresponding with the growth of the mineral. So when we grow these crystals, then we define these various crystallographic direction. Actually, crystallographic directions are the easy directions in which crystals can grow. What is the plane of symmetry in crystallography? When an imaginary plane is passed through a crystal such that the portion of crystal on one side of the plane is a reflection or mirror image of the portion on the other side of the plane, then that is the plane of symmetry. Okay, so if you cut the crystal, if you cut the crystal, if you look at both sides, if the both sides are same, then you can define that as plane of symmetry. What is effective number? The total number of atoms present in or shared by unit cell is known as effective number of atoms. Effective number of atoms per unit cell. Okay, total number of atoms present in or shared by a unit cell is known as effective number. Describe the nearest neighbor distance in the crystal structure. The distance between two nearest neighboring atoms in a crystal lattice is known as nearest neighbor distance. What is atomic packing factor? It is a ratio between the total volume occupied by the atoms or molecules in a unit cell to the volume of the unit cell. Okay. So atomic packing fraction is what is the total volume occupied by the atoms divided by the total volume of the unit cell. That will tell us the atomic packing fraction or the volume occupied by the atoms. Define interstitial or void space or the empty space. The empty space available in a crystal lattice with atoms occupying their respective positions is called the void space. So that is all about the definition and terminology on module 1. And this is the textbooks used and references book to look at. And to summarize, I have discussed the definitions and terminology of module 1, which is crystal structures. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.